All right, so this is about Kirchhoff's rules. So you can see we're opening the OpenStax textbook in that section in the chapter. I'll put this further into the middle here. So let's see. I'll try to get this actually a little bit over here. There we go. So here, yes, they were discovered by Gustav Kirchhoff at some point in the 19th century. I don't know if he invented them. I think he discovered them. But anyway, and I'll talk about them in just a moment, what they are. They apply when you cannot decide if there are two resistors that are really in parallel or in series with each other. For example, are these two here? Well, definitely not in series because there's a junction in between, and then there's a resistor over here. But then the thing is, there's also a battery, and that really makes it hard to analyze. And therefore, the analysis has to be quite a bit more extensive. And what I actually want to say is there are actually two batteries in the circuit. If there was only one, it would be perfectly straightforward, series, parallel. But there are two batteries there, and that just makes it very hard, and we cannot use the parallel and the series analysis anymore. Okay, I will get to that example here in a minute. Just a little thing on the side here, you see that little r right here. This is what's called the internal resistance of the battery or whatever is being used. So let me go back to that supplies the voltage. So let me go back here. So here you can see it. There would be a battery with the internal resistance and what when I say voltage source, yeah, whatever voltage is being used. And when I scroll down here, here would be Ohm's law. So when you have that internal resistance together in series with a normal resistance, which is called the load, then you simply add the two, which is exactly what I'm going to do here. I'm just going to kind of ignore that it's there, but use its value and will add it to the resistance. Okay, so going back here, so what then will happen here is between these two here, these two resistances actually will add. They're in the same part of the circuit. The battery is still there, so we have a battery voltage and we have a voltage drop on the resistor, and then the same thing happens over here as well. And I wish they would have just actually called them here R3 and R3, R2 and R2, something like that, but they didn't. Oh well. Going to scroll down here, and so here we're going to get to Kirchhoff's rules, and there are just two of them, and I think they make really straightforward sense, especially the first one. So the junction rule here, you have a current going into a junction, and then the current that goes out of the junction in the different directions should add up and will add up to the current going in. So 11 obviously is the same as 7 plus 4. That's all that's to it. That's the junction rule. There we go. The loop rule means that when we start at some point and we go all the way around, this could be clockwise as I describe it or counterclockwise, either way, and we come back to the same spot where we started, obviously we arrive at the same potential, the same voltage there. So if I start conveniently at 0 volts and I go once around, I will end up at 0 volts. And so that's the loop rule, that whatever happens here as I add and add and add and add, at the end it comes out to the one that I started with. And again, if I started at 0, then as I add and add and add, I will come up with 0, which means at some point I have to have some negatives in there. Okay, this diagram here is actually kind of nice to show what is happening around. So if I do start at the 0 here, then through the battery from the negative to the positive, I have a voltage increase. And then actually there's a voltage drop. Notice that this is actually plus here and this is minus. So this is more positive. So it goes down. So actually I have a negative going down here. And then I go along here. This is just the wire. And then I have the next resistance. And then this one here goes apparently steeply down. So again, I have a negative here. And then there's another resistance here. And again, I have a negative. And then back to 0. And that's what they're trying to describe here in the equations. Again, straightforward loop rule. You add all the voltage drops voltage increases around a loop, and you come up with the original one, which conveniently ought to be taken as 0. Okay, let's see here. This one is a little bit important. As I said, when you have a voltage drop here, when you have a positive over here and a negative over here, which of course is indicated by the current flowing from positive to negative, notice because of the voltage drop, you need a negative in front of it. Sounds a little bit counterintuitive because you're pointing in the direction of the current, but that means the current is going from plus to minus, which means from a higher to a lower potential, hence a negative is necessary. And if it went the other way, then you would actually have a positive there. The one that we actually analyze, coincidentally, will only deal with going forward with the current as we go around the loop. So we will introduce a bunch of negatives. As you go through the battery, if you're going in this direction here from negative to plus, well, you have a voltage increase, and so that one will be a positive. And if you went the opposite direction, plus to minus, you would actually have a voltage decrease, voltage drop. Okay, so here's the example. And that's what I'm going to calculate. So here we have that, and again the 0.5 here that we see, I'm simply going to add that to the 2.5. These two are in series with each other, so I have a total of 3.0 ohms here, 6.0 in the middle, and 2.0 down here. The only thing that I wish that would be still in the drawing is to signify that this side of the resistor is plus and minus on the other side, so that we have a voltage drop, so that whatever we do here, we're going to get a negative. Okay, same thing on the other resistors, like this one here would be considered a positive, and then here a negative, so as we go around, we introduce a negative. Okay, and then whatever, this one here also, plus to negative, which means if we go this way, right to left in this case, again we introduce a negative. All right, the analysis is already here. Look, it's quite long. I will do it with a matrix. To a certain extent, it's a little bit more visual. I think you'll see that. And then we come up with a result. Actually, the result's already in front of us. Let's see. Oh yeah, problem-solving strategies. These ones here, so yeah, apply the junction rule, apply the loop rule, and so on. There are simultaneous equations for the unknowns. The unknowns are the currents, and I will use the matrix to put them in for the simultaneous equations, because that just makes sense. One little thing here is, we have to assign a certain direction of the currents. We don't know in which direction they're flowing. We can guess. And it turns out that sometimes we actually assign the direction incorrectly of a current. And it turns out it actually doesn't matter. That's why it says here, no harm done. If that happens, all that happens at the end is we're going to get a negative, and we just switch the current around. Really, that's happened. In fact, there is a result that actually will come out to be negative. So to begin with here, we kind of look at this one here. Imagine that there are actually no blue arrows just yet, and you assume that the current will flow from the positive terminal this way, and from the other battery also from the positive terminal this way. So they're going to meet here, they're going to go through this resistor here, and then they split up again. And here we have a junction, and here we have a junction. As already indicated, actually one of those is going to be in the wrong direction, but again, it won't matter. It's hard to tell sometimes in a circuit like that. And once again, third time, it doesn't matter if we have the wrong direction of one of the currents. The result will show us later. Just turn the sign around. Okay, there are three unknowns in here, which are the three currents, which is the current I2 through this resistance, the current I1 through this resistance, and the current I3 through that resistance. So we need three equations to solve for three unknowns. And that means we're going to have a 3x4 matrix, the fourth column being then the result that's on the other side of each equation. For that, we need to analyze the circuit here, and we need to count how many junctions do we have and how many loops do we have. There's a junction on the left, there's a junction on the right. So we have two junctions. There is a loop on the top, this one here. There's a loop at the bottom, this one here. And then there's actually a third loop, which is this what I call the outer loop. There we go. So we have two junctions and two junctions and three loops. Turns out that the two loops are actually identical. Notice that on the left here, the current I1 is going in and 2 and 3 are going out. Well, on the other junction here on the right, currents 2 and 3 are going in and 1 is going out. Well, if you turn it around, left and right, it's the same thing. So these two are actually redundant, which means we can only use one of the junction rules, and then we have to use two of the loop rules. All right, so I'm going to go over here. So this is in my homework, the way I have it set up in there. So here, I copied this one here, and as I said, I just said this a moment ago, so Kirchhoff's junction rule, loop rules allows the analysis, and so on. And then I go in here, so there are two junctions and three loops, 5 equations, but we only need 3 of those 5. Again, the two junctions are actually redundant with each other, so we can only use one. And I wrote it down right there, straightforward. Current I1 equals I2 plus I3. Of the loops, there are 3 loops. I only need 2 of them. I decided to use the upper loop. And yeah, it's when you look at the drawing here from the OpenStax textbook, it's called ABCDEA. Okay, and I decided to use the lower loop. I could have used the outer loop, and as I said, would have been an option as well. Oh, okay, I didn't. Here I set them up. Let's see, I'm not trying to push this out of the screen here. Not just yet, at least. Okay, so this is what I do. I start at the 0 voltage, so 0 potential, and I go up to the battery 18 volts. And you can see that in the equation, there's the 18 volts. Now I'm going to go through the resistor, and as I said, I deal with the internal resistance and this one over here as being the same one. So it is 3 ohms altogether. And you see that here. I2 times 3 ohms. And because I have a voltage drop actually here, I have minus I2 times 3 ohms. Then I continue here, and I'm going to go through R1. And again, I have a voltage drop, so I have minus I1 times 6 ohms. Now someone could say that, well, as I close the loop here on top, I'm going to go through the 2.5 at the end, which means at the end I'm going to subtract 2.5 times I2. Well, if I write it here, and again this includes the internal resistance, or if I write it here at the end, doesn't matter. Okay, lower loop, again I start here at 0 here, and then I go up 45 volts, and this is a little hard to see because one of them is top of the screen and the other one is bottom of the screen. So 45 volts up. Then here we can see nicely, yeah, 3 ohms here, and I have a voltage drop, so 3 times I3, there it is. And then I'm going to go through here, again a voltage drop, the way it's drawn, and I have 6 ohms times I1, and then I return here, and I'm back to 0 voltage, which I wrote here and here. So these are the 3 simultaneous equations. Now I'm going to rewrite these equations so that I only have the unknowns on the left-hand side and the voltages on the right-hand side. So I have I1 minus I2 minus I3. You know, put them on the left. I could also write it negative I1 plus I2 plus I3, same thing. The fewer negatives I have, perhaps the better it is. And then I rewrite these others here. So put just the currents on the left, the unknowns, and the voltages on the right. Okay. Then I'm going to write them in such a way that I can actually use them as in a matrix. So I make sure that I have I1, I2, I3 lined up correctly. So right there, I1, I2, I3. And in the front, I'm going to put what kind of factor each one of them has. Well, there's nothing listed there, but I'm going to put the 1, the negative 1, and the negative 1 there, because that's actually the factor I have in front. You see that one step down when I rewrite it as a matrix, it is already there, so I need that 1, that negative 1, and so on. I'm going to rewrite the second equation here with the I1 in the front, the I2 next. So I have like 6 and then a 3. There it is, 6 and the 3 here. And I'm also going to write the I3 even though it doesn't appear, but I put a 0 in front of it because it's not there. Again, I will need that for the matrix in a moment. And I do the same thing for the third row, and there it is. And now from here I go straight to the matrix. So as I do that, I'm just going to write down the coefficients. That's what I meant to say, coefficients, not factors earlier. And so you see the 1, -1, -1. Those are the currents with the junction rule, and then here are the voltages. So that's the loop rule for the upper one. It's the loop rule for the second one. And now I need to analyze that matrix, and I'm going to do that on a calculator. One other thing to notice here, yeah, you don't notice any units here. I don't need them at this point anymore. In fact, here I need to fix this. Leave out the units. That's what it should say. Align the variables in a consistent order and fill in zeros for these variables that didn't initially show, which is exactly what I said. And I need to put in the word units right there. All right, I'm going to get the calculator. Trying to find it. There he is. There it is. Apparently I did something before. I'm going to go to second matrix. There we go. Go over to edit. I want to have a 3×4 matrix. Plug in these numbers. So 1, -1, -1, 0. Oops, I said 0. I'm going to pause here. So I already took up quite a bit of time already. Okay, it saved me a few seconds. So notice that I put some numbers in here. A couple more. So there's the 2. There's the 45. There we go. Enter, and I'm done. I'm going to go back to the home screen, and I'm going to actually call up that matrix and double check it. What I have here, and if everything is PC, then I can go ahead. All right, so for this matrix, what I'm going to look for is to have in the diagonal here for the 3×3 on the left-hand side 1, 1, 1, and the rest are going to be zeros here. And then I have the results on the right-hand side. So that's what I'm aiming for. And of course, I'm going to use the matrix analysis that you hopefully have learned in college algebra and intermediate algebra, one of those. Okay, so I have a couple of 6s here. That's very convenient. So if I multiply this second row here, I'm sorry, the third row with a -1 and add it to the second one, I get rid of that 6 there, so I get a nice 0 there. So that's what I'm going to do. I'm going to go over here for the matrix and math, and I need my favorite one in here is this one, right? Oh, no, that one there. There we go. Okay, this is how the algorithm is going to work. You see the times row plus. So I'm going to multiply the second row with a -1. Now, what did I say? The third row with a -1. Comma, I tell it which matrix it's supposed to do that to. So that's matrix A. Comma, I said I'm going to multiply the -1 with the third row. What am I saying? Do I keep saying that? The third row, yes. And I add it, comma, to the second row, and therefore I get a 0 there. Boy. Parentheses. Okay, enter, and there it is. Now I got the 0 right here. And then, of course, stuff happened to the other parts in the second row. And by the way, the third row was left alone, even though I multiplied it with that -1, but I only added it then to the second row. There it is. The thing is, I didn't actually save it yet. So here's what I'm going to do. I'm going to do a second entry. It's the same thing. I'm going to save it here in a new matrix, which I then will actually use. I'm going to call it simply matrix B. There we go. And now I have this matrix B. And now if I make a mistake or something, I can always go back to my matrix A, which is the original one. So here it's saved in matrix B. Okay, in fact, let's see, here is matrix B. There we go. Now I'm going to go back a couple of times because on a calculator like this, it's very convenient. So times row plus, let's see, what I'm going to do is I'm going to multiply the first row with -6. And now I'm actually in matrix B, so I permanently will change that to matrix B. And I said I multiply the first row, and I add it to the third row. And then I store it in itself, so I have a new matrix B. And there it is, I got my second 0 there. Next thing I'm going to do is, I'm going to get rid of that 6. There are two choices I could, no, actually there's not, there's only one choice here. Multiply the second row by -2 and add it to the last, and I get a nice 0 there. So again, second entry, and I fixed that, what I have here. So I said multiply -2, the second row, and add it to the third. And I got the next 0 right there. Okay, now I'm going to aim for having a 1 right here, which means I'm going to divide the third row by 12. For that one, actually, I will use a different one. It's this one here, the times. And I'm not going to divide by 12, I'm going to multiply by 1/12. So still a matrix B, comma, and as I said, the third row, parentheses, and store in matrix B. And there we go. So there I got the 1 that I was aiming for. My result apparently is a little bit screwy. That already is one of the results, 8.25 amps in this case. I'm going to get rid of the 3 here, which means, no, that's not true actually. I'm going to get rid of the -2 by multiplying this by 2 and adding it, and I get a nice 0 there. And after that, I'm going to multiply this by 1, add it to this one here, and I get a nice 0 there as well. So I'm going to go back a few steps here because I need to find the other one. There it is. So the last row times actually a +2. That is times the third row and add it to the second row, and you will see I get a nice 0 right there. Now the next thing is get rid of the -1, which means I simply multiply this by 1 and add it to the first one. So 1 right there. Let's see, third row still, and now the first row. There we go. All right. Okay, next thing to do is I divide the second row by 3. So again, I'm going to go back to this other one that I had. A few steps back right there. So as I divide by 3, I actually multiply by 1/3. And this is just the second row, and you will see we get a nice 1 in the middle there. There it is. And the very last step is to add the second row to the first row, so I get a nice 0 there, which means I actually multiply the second row by 1. Right there. Second row, the 1 is already there. Add it to the first row. There it is. Enter, and I'm finally done with that. So that is the matrix analysis for a Kirchhoff circuit, where, yeah, it just doesn't get easier than that. They are that actually complicated, and someone is in electricity and trying to figure out electronic circuits, they have to do that. Of course, they have a computer available. I did that here. By the way, little afterthought, watch this. After I did all these steps, and here are the results, right? Let's see, I'm gonna clear this here. Remember those results, right? I do this. There's a double REF. There we go. Oops. Clicked on the wrong one. Come on. Double REF. There we go. Matrix A, because that was the original one. And then actually it does all the steps in 1 second. But I wanted to show you that, hey, there's some work involved here in order to do that. If we're in the lab, we're actually more likely going to use this one here, the quick way, but you need to understand the way it's originally done. So we have 4.75 amps in I1, negative 3.5 amps in I2. That's the one that actually flows in the opposite direction. And then 8.25 in I3. So when I go back to the original drawing, there it is. So this one here, I3, that's the 8.25 amps. The R1 here, I think that was the, how much was it? 4.75 amps going this way. And then this one here is actually the negative 3.5 amps, which means it actually flows in the opposite direction. And on second thought, if we look at this, this one has 45 volts, which really opposes the 18 volts up here. But again, we didn't know that earlier. Okay, I'm going to go over here to actually the circuit FET, PHET, and I think, let's see, we can see that right there. So I already set it up. Here's the battery, 18 volts, 45 volts, and here we have the 3 and the 6 ohms, the 2 ohms. And yes, the internal resistances, I simply added them over here to the 3 and to the 2 over here. And I'm going to close the switch and the other switch. And notice that on the top, in just a moment, when I turn this one here, even though I have the positive terminal here, the current is not going to flow to the right. Watch. There we go. It actually flows in the opposite direction of the battery. Notice actually when I open the switch at the bottom here, that's not the case. Now it really flows in the direction it's supposed to. But with these two switches closed, then yeah, the 45 volts is just too powerful here, so it actually pushes the current in the opposite direction. Okay, let's see what the currents are. I gave it the correct numbers here. Here's the I3. Indeed, it is 8.25 amps. Here it is indeed 4.75 amps, and here it is indeed 3.50 amps. This particular ammeter does not discriminate in which direction that is going. This is also a no contact ammeter where you simply clamp it around the wire and you don't have to interrupt the circuit here. Works with the magnetic field that is being produced by any kind of current and the Hall effect. All right, that's it for Kirchhoff's law, and I noticed that, wow, this was a long one here. 27 minutes is what I have recorded for just this one.